Okay, so it's now my pleasure to introduce the next speaker, Dr. Sally Liu. She's the Technical Director of Mixed Signal RF Solutions Division at TSMC, and she is a graduate of our department, Berkeley ECS, and she did her thesis on MOSFET models for SPICE, and this was under the guidance of Professor Don Peterson. Yes. And let's welcome Dr. Sally Liu.
It's my pleasure to be here to talk about compact modeling. That's one of the major cornerstones of Chanming's contribution, accomplishments. My talk divided into 4 parts. First, we'll examine what is BSIM. It's really more than what it is. It's an industrial standard, and then we also examine its breadth and depth. I will conclude with my view on what will happen to compact modeling as we move forward. Okay. Well, what is BSIM? Certainly, it's made of all the hard works by Chanming's team. And I peek into the IEEE's database. Wow, there are totally 631 papers by Chanming's team. Certainly, early on, the paper is more about into the reliability area. And then the first IGFET modeling paper was published in 1984. That's the charge model. And later on, in 1987, the BSIM's name is formally coined. It stands for Berkeley Short Channel IGFET Model. At the time, MOSFET is called IGFET, insulated gated field transistor. And look at today, Chanming has grown a BSIM family. We have successions of models for planar MOSFETs, from BSIM all the way through BSIM 6. And then there are FinFET models. You already have BSIM MG, BSIM CMG, BSIM IMG, and there are also SOI models. And this is a tremendous accomplishment. With the publication of the first 2 papers on IGFET models, BSIM was born. Well, actually, a compact model is really just a tip of iceberg. A compact model embodies the results and the wisdoms of many disciplines. First of all, the device needs to be invented and fabricated and understood, its operation be understood and formulated in mathematical equations. And once the model is proved in the laboratory, it needs to be transformed into software programming. Or the T need to be crossed, or the I need to be dotted, so that it will converge in SPICE. So it's a collaborative effort of many disciplines to make a compact model. And actually, today, academia and the industries, they are all bending on this. And well, so how great is BSIM? What's BSIM's impact? Is that just word of mouth? So I try to have some rich numbers to size up BSIM's impact. I look into the IEEE's database again. Totally, there are 200 papers with BSIM quoted, either in their title, or in their keywords, or in their abstract, or embedded in their text. I don't know if there's any other models being quoted so often. You may think they are all by Chanming's team. No, actually not. There are only 28 of these 200-some are by Chanming's team. There are 40-some from the industry. Most of them are by the academias. There are 150. Essentially, as being a standard model, it also becomes a golden platform for the universities to proceed their research. Well, yes, one important accomplishment and impact of BSIM is being the first industrial standard MOSFET model. Well, the compound modeling effort, a standardization effort, really starts before 1996. That's a time of fragmented compound model developments. Even though there is a so-called de facto standard, but there are different flavors of MOSFET models in all alphabet spice. And at that time, the fabless foundry are small guys, and the big guys are the IDMs. They all have their proprietary model and the tools. So the cross-team design transactions are quite chaotic. And in the early 90s, there is a collective effort sponsored by Compact Modeling Council, CMC, to elect the first MOSFET standard model. Extensive benchmarking with cross-industrial collaboration was happening. And the BSIM team's dedication, led by Chen Ming, is a key for its acceptance by the industrial-wide. Actually, if you go to CMC's website today, you will claim it was founded in 1996. But actually, the whole process of electing the first MOSFET standard model really happened before that. So BSIM also changed the history of CMC. Certainly today, there are more models in the BSIM family becomes the industrial standard. BSIM 4, the next generation for nanometer effect, becomes standard in 2000. And the BSIM SOI is a standard in 2002. And BSIM CMG for the FinFET becoming a standard just this year. Well, that's how BSIM, that's the first impact of BSIM as a standard. And now, for now in the future, I want to point out another critical role of BSIM is BSIM is the first standard model that is supported by CMC's first standard model API, application program interface. That is critical. The basic concept of the API is to add additional layers to describe the interaction of the device with its environment on top of the intrinsic model. And the intrinsic device has to be described by an intrinsic model that's BSIM. Yeah. And the BSIM 4 is the first standard model in the first standard API. And macro modeling, yes, and it has been proven to be efficient, make the macro modeling simulation very efficient, including speed up of the setup time in SPICE simulator, the memory usage, and the computation time, all drastically improved through using API. I want to say a few more words about macro modeling because it is very critical for compound modeling at the nanometer. It can be used to build a very good modeling, complete compound modeling layers on top of the intrinsic models. Like today, that's happened with all the stressors put around the MOSFET. There's a very complicated interaction between the device and its environment. So there's a very complicated layout dependency effect. Macro modeling is a good way to manage it. And then today, there's also the local interconnect required to connecting the device out. This middle layer interconnect. Its impact also can be effectively modeled using the macro model approach. Well, with the advanced LISO, there are very complicated and restricted design rules that also need to be enforced through the modeling channel that can be handled also at the macro modeling level. And the statistical parametric, the variations, and the self-heating effect, all those extrinsic stuffs, and aging effect, and the additional geometry scaling, like the so-called half node. This also can be easily accomplished through macro modeling. Yeah. Okay. this, I forgot to show the cartoons. Yeah. Yeah. And so to sum it up, okay, this is this original diagram is made by my colleagues in litho. This described their view of how the litho progressed from mid-70s all the way to now. Okay, the dotted line is the references, and then the blue line is their projection of the end of optical litho. You can see that they are very pessimistic all the way along, but actually the optical lithography is still going strong today with the immersion. Well, at the beginning, certainly before BSIM, there are compound models in SPICE from Berkeley, but that's not enough at the time when my litho colleagues are struggling to go from 248 to 193. And then BSIM was born, and in the mid-80s, and then in 96, BSIM 3 version 3 became the model, standard model, and then 2000 BSIM 4, and then 2002 is the BSIM SOI, and then in 2010 the API becomes the standard interface, and today this year the BSIM CMG also becomes the standard model. And currently, there are new nanometer effects, the high kinetic effects that also need to be embodied. I think the BSIM 6 currently is being seriously considered by CMC to become the next standard model. And throughout these green blobs are highlighting the years that Chinese team are very, very productive in terms of the publications. They are, every year they have many, many publications. Okay. Now I want to use lay on top of this plots on the on the models evolved throughout the time. Right, BSIM, based upon the information embedded in the IEEE database. Okay, BSIM 2, BSIM 3, BSIM 4, BSIM 5, and then BSIM 6. That's for planar. Then there's also developments on the compound models of SOI, BSIM PD, BSIM SOI, and this is for FinFET, right, all the way till now. Okay, and the reason BSIM can continue to be the primary workhorse of the MOSFET model because it continue to evolve as the technology evolves and embodies many critical nanometer effect. Well, so this is just an illustration of the critical features in BSIM 4. Currently, that's the workhorse model of TSMC models. The BSIM 4, and then there is the layout dependent effect, okay, and well proximity effect, and the compounded LOD effect, and then more strength silicon induced stress effect, and up to this age, right, we rely on macro modeling to rein in all this complicated layout dependent effect. Okay, and the page, the previous page really just highlight the critical effect. Actually, it's built on top of a very solid foundation of all these basic features. The list, I wouldn't say exhaustive, and as you know, all the T need to be crossed, all the I need to be dotted, so that every effect that will be congruently embodied into the simulator and converged while you simulate. And that's a very, take a lot of dedication of many talented people in Chinese team. Yeah. And that's just what we have now, actually looking forward. there are more newer effects that need to be running, like the new device structure, okay, and then layout dependency factor and variation percentage becomes larger. The spatial gradient also need to be considered. And the radiant telegraph, noise, self-heating, and aging effect. All this, right, need to be continued to build into the compound model as they become so critical to the nanometer circuit design. Yeah. To sum up BSIM related evolution and revolution. Well, in foundry, we have adopted the BSIM model since it's an industrial standard early on, and we pace our modeling developments with the Berkeley team. 2003, we adopted BSIM 4.3, and in 2004, we adopted BSIM 4.4, and 2005, we adopted BSIM 4.5. And it started in 2007, right, with the compound LOD effect happened in 40 nanometer effect. We start to use a subcircuit to build the macro models and continue to do that in 2008 for 28 and 20 nanometers. As TMI2 becomes the standard modeling interface, we start to experiment that, beta testing it for deploying the aging model into the FinFET. The most noted, one of the most noted accomplishments from Chairman's team is the invention of FinFET. Early on, Clement quoted the paper in 1996, and later Chairman talked about 1999. And here I quote the paper of 1998. I think all this says that the heat was on in the Berkeley team at that time, that duration of time, leading the revolution of FinFET. And it also see it through to see it become a viable transistors for sub-20 nanometer technologies. And definitely see through that its compound model also become a CMC standard. Well, moving forward, right? No matter will be working with 2D, 3D devices or the post-silicon devices, I think compound model will continue to play a very critical role in the design enabling. That will, moving forward, they will require more intensive collaborations between the foundry and the design. And our early customers are coming in early, even ever early on, because it's very, the device interacts with the environment much intensively. So all the details need to be jointly looked at early on. And then the model, compound model becomes a viable communication channel and the vehicles to construe the collaboration. Yeah, and then definitely the standard we would need, BSIM-like standard models continue to model the intrinsic device. And then the modeling interface will be deployed to efficiently to build a macro model to capture the interaction between the device and its environments. Yeah. In the semiconductor ecosystem, right, from product definition all the way to the product shipped to the marketplace, the compound model and its parameter are the most critical link in all this product information, design information, and transactions. And it will continue to play this role. And we'd like to see the Berkeley team continue to help the industry in this regard. Yes. And with the, one thing is for sure, only one thing is sure for the future, is there will always changes. The new changes will happen much faster. And the only way to cope with that is to have an open technology modeling platform such that the the design and the technology people can collaborate more intensively to foster much more innovations for the future. This is all I have today. And at the end, I want to acknowledge contributions from my colleagues, Min-Chi, Bing, and Ke-Wei, and CK. If you notice that Min-Chi and Bing was the first author of the first BSIM papers, and Min-Chi is also the co-author of the first papers. This is all I have. Thank you very much for your attention.
I can tell stories about Sally. I think we'll save that later because I think this topic particularly requires me to acknowledge some other contributors. There's a couple of things separate BSIM research from the other things that this group has done. One is that we first benefited and we try to support a very proud tradition of Berkeley ECS department started in the EDA side from Professor Don Peterson. He provided the SPICE model free to the industry, and that really put Berkeley on the map, so to speak, as the leading university for the EDA. So we followed that, and that also partly explains the success of the BSIM and continue to bring reputation to Berkeley. But because of that, the students, postdocs that have worked on this project actually had to do more grunt work than other type of research. A lot of things about the quality of the code, robustness, speed. And so we really should mention a few persons. One person in the room, I think is Jian Hui. Jian Hui are still here? Yeah, there. Jian Hui is the author of BSIM 3. BSIM 3 is special because that one really putting a lot of the physics that Pinko, myself, and many of the students present developed. We didn't really have the compact model in mind. It's just important to understand the transistor physics, but Jian Hui put that into that, so that really blew the other compact model away and became the first standard. Of course, after that, it's easier for us to continue to do the same thing. And the good news for that is that, you know, most of our compact model students, postdoc contributor are not, they have wide open opportunities for them. Just want to make one mention that the last two BSIM students, Chongqing is here, Arsen is here, Chongqing Chen, they developed the feedback model, and they are actually leading the most advanced transistor development at IBM. So this is what is good about this. I think other people that have contributed very quickly, just by looking, scanning through the room. I know James contributed to that a lot. Bing-Su, Samuel, and I know I forgot many.
Dunga's there. Dunga.
Dunga, of course, yes. And Yang-Qing's models, so I really want to acknowledge all the contributors here. Thank you. And thank you, Simon.